Signal conditioning with the use of difference amplifiers. If you look at this diagram, you can see that there is an operational amplifier with the resistor R1 and R2 in the inverting inputs, and also the same sized resistors are on the non-inverting input. And we have signal V1 on the non-inverting input and on the inverting input, and signal V2 on the non-inverting input, and then we have the output voltage. What is interesting about the difference amplifiers is that they amplify the difference between the two input voltages, and there is virtually no current between the inputs of the operational amplifier, which means that there is no potential drop between the inputs, the inverting and the non-inverting input, so that both these inputs are at the same potential, and thus we can say that the input signal V2 voltage is equal to the voltage sum of the voltage drops over resistors R1 and R2. This gives that we have voltage division in node X, where we can say the ratio of the voltage in node X and the input signal V2 is equal to the ratio of resistor R2 divided by the sum of R1 and R2. And this in turn can see that because there is no potential difference between the inputs, that the current in resistor R1 and R2 are equal, and that if we apply Ohm's law for the current, we can see that the voltage drop over the resistor 1 divided by the resistance is equal to the voltage drop over the resistor R2 divided by the resistance. And if we rearrange this equation to isolate for the output voltage, then we end up with an equation where we can say that the output voltage is equal to the ratio of R2 divided by R1 times the difference in input signals. As an exercise, you should try and solve these equations to see if you can get the same results. Now again, if we take a application example for a difference amplifier, we can have a circuit where we have a thermocouple connected between the inputs, as shown on the figure. If you don't know how a thermocouple works, then you can try and search for information on that. But what we want to know here is that the difference in voltage between the EMFs of the two junctions of the thermocouple is being amplified. If you look here closely, you can see on this circuit diagram that we have here marked V1 where the hot junction is connected, and V2 where the cold junction is connected. And these two, V1 and V2, go to respectively to the inverting and non-inverting inputs of the amplifier. We need to select resistors R1 and 2 so that we want to select R1 and R2 so that for a 10-degree difference between the thermocouple junctions, we get an output signal of 10 millivolt. And we know that a 10-degree difference between the junctions gives a difference voltage of 530 microvoltage on the difference on the inputs of the amplifier, then we can use this equation which we have here, where we say the output signal is equal to the ratio of R1 divided by R2 times the difference in input signals. And if we fill into this equation and we say 10 millivolt equals the ratio of R2 divided by R1 times these 530 microvoltage, then we end up with that the ratio of R2 divided by R1 is 18.9. And by selecting R1 to be 10 kilo ohms, we can find that R2 equals 189 kilo ohms. So with this calculations, we have designed a simple signal conditioning circuit with a difference amplifier, where we have found the resistors to be used in this circuit. Now, there are, for difference amplifiers and amplifiers, op-amp amplifiers in general, there are two conditions that I would like to explain here. One is the common mode voltage and the other is the common mode rejection ratio. When we use a difference amplifier with, for example, a Wheatstone bridge that is constructed with strain gauge sensors in its arms, then to amplify the out of balance potential difference, when the resistance in one or more of the arms changes, it can be seen that for a non-ideal amplifier in practice, the output voltage is not proportional to the difference between the two inputs. To account for this in calculations, we can say that the output voltage is equal to the gain of the voltage difference between the inputs plus the common mode gain for the common mode voltage times the common mode voltage. And if we look closely at this equation, we can say that the smaller the common mode gain, then it has smaller effect on the output voltage. And to explain, then the voltage difference is the difference between the voltage at voltage potential at the non-inverting input minus the potential at the inverting input. And for the common mode voltage, you can say it is the average of the potential on the inputs of the operational amplifier. How much op-amp deviates from the ideal behavior is determined by the common mode rejection ratio, where you have the gain for the voltage difference and the common mode gain. And you can see that the higher the common mode rejection ratio gives a lower effect on the common mode voltage, on the output voltage. And typical values of the common mode rejection ratio is between 80 and 100 decibels. And if you in datasheets encounter a large number like this one, 10,000, you can calculate it by saying 20 times the logarithm of 10,000 gives you 80 decibels. Thank you.